today I'll be discussing about the pass transfer logic. So now let us take a look at how this transistor behave in series and parallel connections. So here we have two NMOS transistors connected in series. The output Y will be equal to X only if both A and B are logic 1, and in this case they are connected in parallel. So Y will be equal to X if any of A and B are logic 1. And now the case of a P MOSFET. So here we have two P MOSFETs connected in series. So the output Y will be equal to X if both A and B are logic 0, and if they are connected in parallel, this output Y will be equal to X if any of A and B are logic 0. So now the pass transfer concept. So here there are inputs, and this output will be obtained based on switch networks. So switch means the transistors. These transistors have gate and source and drain terminals. So in pass transfer logic, all these terminals are driven by the primary inputs itself, means A, B, C, like that itself. In contrast to the CMOS technology. In CMOS, the drain and source are connected to the VDD and ground power rails. So now let us take an example of OR gate. So in OR gate, you know that either A or B are 1, the output will become logic 1. So how we can design a pass transistor logic for OR gate? So I have two transistors, and these two transistors will be working based on the primary inputs A and B. So now ground and VDD are connected to this. So for P if B equal to 1, the output logic F is 1 itself. Means that, so if you are having gate B to this N MOSFET, so we are giving B as the input because B and F are same. And for B bar, so B bar equal to 0, B equal to 0. Here the output function is equal to A, right? So we'll connect for this transistor B equal to 0, B bar equal to 1, and then the output function is equal to logic A. And this is how we create a pass transistor logic. Now take another example of AND gate. So we have AND gate truth table. So output of AND gate will become 1 only if both A and B are logic 1. So we have two transistors here also, and when B equal to logic 1, the output will become A itself, right? Output will be A itself. So for B, when this gate is turned on, when B equal to 1, the output function will be A itself. And for B bar equal to 1 means B equal to 0, in this case the output function is also 0. So for B bar case, this transistor will be turned on and B, which is equal to 0, right? And this 0 will be transferred to the output function. So this is how we realize an AND gate. Now the case of an XOR gate. In XOR gate, the output function will be equal to logic 1 when any of the inputs are logic 1. When both are zeros and both are ones, the output will become 0. So here, if B equal to logic 1, the output is the inverse of A, right? So when B is turned on, this transistor will be turned on when B equal to 1, and the output function will become A bar. And for the other case, for B bar case, the output is A itself. So for B bar transistor, the output function is equal to A itself. This is how we realize an XOR gate. Now we have some problems for you. Please realize these three gates: NAND gate, NOR gate, and XOR gate. So the advantages of pass transfer logic here: the gate is static and there is a low impedance path exists between the power supply rails. And another big advantage is less number of transistors. So we have only n number of transistors instead of 2n in contrast to the CMOS technology. And another is there is no static power consumption because there is no direct connection between VDD and ground rail. And the ratio-less. In CMOS technology, we need to keep some W/L ratio and also pull up to pull down ratio. Here we don't need that. And another advantage is bidirectional. So there are some disadvantages. One disadvantage is the logic is regenerative, and the signal will gradually degrade after passing to the transistor. So if we use a PMOS transistor, it will pass strong 1, but the 0 will be degraded. And if we use NMOS transistor as switch, so it will pass strong zeros, but it will weak the VDD or logic 1. So how it will do that? So we have a NMOS pass transistor. So if you are giving a VDD here and VGS is this, and we have this output capacitor, this is a load. So this VGS will be, this transistor will be turned on when this VGS is greater than VTH, and it will cut off when this VGS means the voltage difference between gate and source. And when this is smaller than VTH, this transistor will be turned off. So when we are giving this VGS as a high voltage, this N MOSFET will be turned on, and the current will flow through this transistor to this capacitor or the output load. And when this point, output point, is charging up, and when it is charged to a point VDD minus VTH, so this is the output point or the voltage at source, and this gate is at a voltage of VDD, right? So this VGS is equal to VG minus VS will be equal to VDD minus VDD minus VTH, and that will be equal to VTH. So if this capacitor is charging greater than VDD minus VTH, what happens? The voltage which comes across VGS will be smaller than VTH. It means that this transistor will get turned off. So that's a problem. So the maximum voltage that can be charged at this point will be equal to VDD minus VTH. So instead of VDD itself, we're getting so our logic 1 at the output side will be VDD minus VTH. Similarly for a PMOS transistor, here logic 0 will be degraded. So this will create a problem if we cascade our BTL logic. So here the output of one MOSFET and MOSFET is connected as the gate of another MOSFET. So here this point X can only charge up to VDD minus VTH of first MOSFET, right? So this is the maximum voltage that can appear at this point. So since this is connected as the gate input of the next M2 transistor, the voltage that can come at this point is equal to VDD minus VTN1 minus VTN2. So it is cumulatively degrading. So how to restore, or how the solutions for these problems are: one is using a restoring transistor just like a pull-up transistor, and another is a single transistor pass gate with a threshold voltage, very low threshold voltage, and another is a transmission gate. Thank you.